Welcome to Physics Corner, Motion Part 3 for secondary school physics, and the topics to be covered are velocity time graphs. Looking at the velocity time graph with velocity on y-axis and time on x-axis, we would discuss 6 different cases. Looking at the first 2 cases, first graph shows that at time t is equal to 0, the velocity is 0, and as time progresses there is no change in velocity, which means it has remained 0 permanently. And in the second case, initially there is some velocity. At time t is equal to 0, the velocity is not 0, which means the car is already moving. And as time progresses there is no change in velocity, which means the car is traveling at constant velocity. Hence, the horizontal straight lines for velocity time graph shows either the car is at 0 velocity or the car is at constant velocity. Let's look at the third case and fourth case. Let's take this as a third case. Initially, the velocity of the body is absolutely 0, and as time progresses, there is a steep increase in velocity, that too at a constant rate. Why I said constant rate is because it's a straight line. A straight line always shows a constant increase of the function. Hence, the velocity is increasing at a constant rate, which means it's uniform acceleration, which means uniform increase in velocity with respect to time. Let's look at the fourth case. Initially, the velocity is not 0 here. It has got some velocity. That means the car is already traveling at the velocity when you have considered the analysis. After some time, the velocity has decreased, and the decrease in velocity is also at a constant rate, which means it's a uniform decrease in velocity, which we call it as uniform deceleration. So in common, we can say case 3 and case 4 would come under uniform acceleration and uniform deceleration. Let's look at the fifth case, in which initially the body shows steep increase in velocity, and then at a sudden there is a huge increase in velocity in a small interval of time. Till here, the body has shown constant increase in velocity and then a sudden increase in velocity, which means it's not uniform acceleration, it's increasing acceleration, because the velocity has increased to a greater values in a very short interval of time. So it's increasing acceleration case. Let's look at the sixth case and the final case, in which initially the body shows uniform acceleration, that is increase in the velocity at a constant rate, and then the increase in velocity becomes slower. Increase in velocity becomes slower means there is no much increase in velocity in a longer amount of time. The velocity did not increase much. If it increases much amount, it would have been a graph where it goes straight like this, but actually it's showing a saturation point where the body is not increasing its velocity anymore, hence it is decreasing acceleration case. So case 1 where the body is at rest permanently, case 2 where the body maintains constant velocity, case 3 where the body maintains uniform acceleration, that is increase in velocity at a constant rate, case 4 the body maintains uniform deceleration, there is a decrease in velocity at a constant rate, case 5 the body shows increasing acceleration, and case 6 the body shows decreasing acceleration. Let's have a look at what exactly the slope of velocity time graph gives you. To do that, let's analyze the case of uniform accelerated body, uniformly accelerated body, for which the velocity time graph is a straight line. So this straight line reflects that the body is under uniform acceleration. To find the slope, let's take some amount of time period during which the body must have increased its velocity by delta v. Initially the velocity is 0, after some time the body has got some velocity, hence let it be delta v. So the ratio delta v by delta t gives you velocity over time. So this ratio is nothing but acceleration, which is increase in velocity in a certain amount of time. Hence, the slope of velocity time graph gives acceleration. Next thing, what does the area under this graph gives you? The area under this graph is all about the multiplication of both the coordinates, the velocity and time. Velocity multiplied by time, or simply speed multiplied by time, gives you distance or displacement. Hence, the area under the graph, if you find the area under the graph, in this case it's a very simple right angle triangle which can be found very easily. The area under this graph always gives you displacement, and this concept we would be using in deriving the equation of motion of uniformly accelerated bodies. So it's very important. The area under velocity time graph gives displacement. Let's try to solve a problem to find which of these two bodies, car A and car B, has got the highest acceleration. And to do that, we would consider the concept of slope for a velocity time graph, which gives us acceleration, because we would like to find which of these two bodies has got the highest acceleration. So it's always best to use this equation, which gives you change in velocity by change in time. This reflects the acceleration. But for that, let's consider a vertical line passing through both the graphs at time t. And if you would like to know the velocity of car B at this time, you have to have a horizontal line for that, which is assumed to be 10 meters per second. And if you would like to know the velocity of car A at the same time, you need to have another horizontal line here, which gives you a value which is less than 10, because it is supposed to be below it. So let's assume it as 5 meters per second, which clearly reflects car B has attained the velocity greater than car A in the same amount of time provided. Hence, car B has the highest acceleration. Now let's have a look at the concepts of uniform acceleration and retardation through velocity time graphs. Let's have a look at this particular graph. For a body whose initial velocity is not 0 but a certain value u, as time progresses the velocity is decreasing uniformly, and after some time t the velocity became 0. Hence, initial velocity is u and final velocity is absolutely 0. Hence, we can say the body is under uniform deceleration. We call it as uniform because it's decreasing at a constant rate. You can observe this particular case practically in case of a body projected vertically upwards against the gravitational pull. When you project a body vertically upwards at a certain velocity, you have to give some velocity to it. Let's say that's the initial velocity we should give to it. As it starts moving vertically upwards, it loses velocity continuously at a constant rate because of the gravitational pull of the Earth or of any planet. At the maximum height, the body would reach to a maximum height and attain a velocity which is absolutely 0. That means the body would come to rest at the maximum height possible, and at which the velocity is obviously 0. So the best example for a uniform deceleration case is the body projected vertically upwards. Let's have a look at this graph in which the initial velocity is absolutely 0, and as time progresses the velocity is increasing uniformly, and hence we can call this as a uniform acceleration case. And the practical case for this is the freely falling body. Once you project a body vertically upwards, it would reach the maximum height and attains a velocity 0, and then the body starts falling freely under the attraction of gravity. Hence, it increases its velocity at a constant rate, and we call this case as uniform acceleration case. That's it. Motion Part 4 for secondary school physics, and the topics to be covered in the upcoming part are acceleration time graphs and uniform circular